what if instead of looking for the area, I was given the area? Or instead of looking for a probability, I'm given a probability and I want to find the z score that has that area to its left. Then remember, normal CDF gives me a probability. That's not what I want here. I'm going to be given a probability. I'm looking for a z-score, and whenever that is the case, I go one down below normal CDF on the VAERS menu or the distribution menu and choose number 3, inverse norm. When I choose inverse norm, I always, always, always have to enter the probability to the left of the desired score. In other words, um, if I'm looking for this z-score and I tell you the probability to the left is zero point 0.7, then zero point 0.7 is what you'll enter inside that parentheses. But if instead of giving you the zero point 0.7, I give you zero point 0.3, the probability to the right, then you're going to have to find the probability to the left and enter the probability to the left on the calculator. You always enter the probability to the left of the z-score that you want. All right, example 6 is using the same thermometers with a mean reading of 0 and a standard deviation of 1. Find the temperature corresponding to the 95th percentile. We have to think about what 95th percentile means. We have the mean temperature reading is 0, and we're not looking for a probability here. It doesn't say find the probability or find the area. It says find a temperature. A temperature is a z-score. And we want to find the temperature that separates the bottom 95% from the top 5%. Where do I need to make a vertical line if I want 95% of the area to be below it? It's going to have to be over here somewhere. I'm looking for this temperature that has an area of 95% to the left, or a probability of 95% to the left. Since I'm given a probability and I'm looking for a z-score, that's when I use inverse norm. And I enter the 0.95 because it's the area to the left of this z-score I'm trying to find. So second distribution, we're looking for a z-score, so we're going to use number 3. And the area to the left of the score we're looking for is 0.95. The z-score we're looking for, if we round it to 2 decimal places, is 1.64. If we use 1.64 as our z-score, then 95% of the thermometers will have readings below that. And that's what 95th percentile means. Now, just for the heck of it, let's prove, or let's say, if we were just given this z-score and the question was, what is the probability that a thermometer would have a reading below 1.64? If we were looking for a probability, then we would use normal CDF and we would say, what is the probability that a thermometer would have a reading less than 1.64? That means a reading from negative 9,999 up to 1.64. It's about 95%. These two operations, inverse norm and normal CDF, they undo each other. If I give you a z-score and ask you for a probability, then I should be able to check that by giving you a probability and making sure that I get back the same z-score. You use inverse norm when you're looking for scores. You use normal CDF when you're looking for probabilities or areas. 95% of the thermometers will have a reading less than or equal to that temperature we found, 1.64. If 2.5% of the thermometers are rejected because they have readings that are too low, and another 2.5 are rejected because they have readings too high, find the readings that are the cutoff values separating the rejected thermometers from the others. The word that tells me to use inverse norm rather than normal CDF is this doesn't say find the probability or area, it says find the readings. That tells me to use inverse norm. And on every problem in Chapter 6, I'm going to draw my normal distribution so I can determine what numbers to enter after inverse norm. The mean reading for these thermometers is 0. I want the cutoff scores that separate the bottom 2.5% from the rest and the top 2.5% from the rest. Let's talk about this bottom 2.5% first. There is some z-score that only has 2.5% of the thermometers with readings below that z-score. That percent, that's giving me a probability or an area. When you see percent, I want you to think probability, area, percent, same thing. That 2.5% corresponds to an area right there of 0.025. I want the z-score that has 2.5% or 0.025 to the left of it. Since I'm given that probability to the left, 0.025 is what I enter on the calculator. Inverse norm, second distribution, number 3, inverse norm, 0.025 is approximately negative 1.96. So if I use negative 1.96 as the cutoff for the lower end of acceptable thermometers, then only 2.5% of thermometers will be rejected for having readings below that. Thermometers will be rejected if readings are less than negative 1.96. And I could do something similar to find the upper cutoff score that only has 2.5% above that. Now there's two ways to find this, and you just need to be careful. If you have 0.025 to the right of the z-score you're looking for, then you have to forget this line for a second and say how much of the area is to the left of the z-score that I'm looking for, because I always have to enter the area to the left. Well, if the area to the right is 0.025, then the area to the left of that is 1 minus 0.025, or 0.975. To get this z-score, I'd have to enter inverse norm 0.975, because that's the area to the left, and that's what I always have to enter with inverse norm. Inverse norm 0.975 is positive 1.96. But actually, I should not have had to use inverse norm again, because I know this is a normal distribution. I know there should be the same area to the left of negative 1.96 as there is to the right of positive 1.96. So if I've already found this z-score that has an area of 0.025 to the left is negative 1.96, then when I'm looking for this z-score on the right, I should know that it's going to be just the opposite of this z-score because there's the same amount of area to the left and to the right. Thermometers will be rejected if their reading is less than negative 1.96 or greater than positive 1.96. There's only one other thing in this section, and it is also finding a z-score, but it's a very particular z-score called a critical value. Critical values are going to be important in Chapter 8. So let's talk about what a critical value is. A critical value is a z-score on the borderline separating z-scores that are likely to occur from those that are unlikely. Unlikely. Common critical values are negative 1.96 and positive 1.96, and they are obtained as shown in the previous example. We're going to use other z-scores, but negative 1.96 and positive 1.96 are going to turn out to be very common numbers that you'll see. In the previous example, the values below negative 1.96 are unlikely to happen. They only occur in 2.5% of the readings. Or X values above 1.96 are unlikely to happen. They only happen 2.5% of the time. The reference to critical values is not as important in this chapter as it will be in Chapter 8, but we're just learning the notation and how to find it. So this expression, Z sub alpha is a critical value. And specifically, Z sub alpha is the z-score that has an area of alpha to its right. That's very important. If I draw a normal distribution, and I ask you to find Z sub alpha, because I'm asking you to find a z-score, you're going to use inverse norm. But the definition of Z sub alpha is the z-score that has an area of alpha to its right. Well, we just talked about inverse norm. When I use inverse norm, I can't enter the area to the right. I have to enter the area to the left. Well, if this area is, let's say, 0.2, then how can I find the area to the left? It would be 1 minus 0.2. If this area is 0.2, then this area is 0.8. Or if this area is alpha, then this area is 1 minus alpha. And because I always have to enter the area to the left, when I have the instructions find this z-score, I have to enter inverse norm, not alpha, but 1 minus alpha. Be very careful on the calculator, since inverse norm alpha would give me the z-score that had alpha to its left, and that's not what I want. I want the z-score that has alpha to its right. So I have to find the area to the left before I use inverse norm. Let's do an example of that. The directions simply say find the critical value Z sub 0.02 for the thermometers previously described. Now, what does Z sub 0.02 mean? That means find the z-score that only has an area of 0.02 to its right. If it only has an area of 0.02 to the right, it's going to be over here somewhere. But again, the definition of this notation, this z sub 0.02, is that 0.02 is the area to the right of the z-score that I'm looking for, and that's not what I can enter in the inverse norm. If you give me the area to the right, I'm going to have to subtract to get the area from on the left, and that's what I'll enter in inverse norm. Not inverse norm 0.02, but inverse norm 1 minus 0.02. To two decimal places, that's 2.05. Now, if I could go ahead and say a dollar minus 2 cents is 98 cents or 0.98, then I could just enter inverse norm 0.98 on the calculator. But if I had a number I couldn't subtract from 1 in my head, then I can still enter inverse norm 1 minus that number, and the calculator will do the subtraction before it applies the inverse norm. Z sub 0.02 equals 2.05 means that the probability of a thermometer reading more than 2.05 is only 0.02, or only 2% of the thermometers will have readings above 2.05. It wouldn't be a very accurate thermometer if it was more than 2 degrees off. It's supposed to read 0 at freezing point. If it's reading 2.05, it's more than 2 degrees off, and only 2% of the thermometers would have readings above that.